Dr. Sanjeev Nandedkar is joining us from New York State. He's a senior consultant and clinical application specialist at Nyquist Neuro. He also teaches and conducts workshops at many international meetings. His primary research interest is quantitative analysis of the signals recorded in electrodiagnostic testing, and he will speak about standards of instrumentation of EMG.
Good morning, good afternoon, good evening, wherever you are. And thank you for inviting me to give this talk. I'm going to talk about standards for instrumentation, which has recently been very nicely summarized in this publication. Most of what I'm going to discuss can be found in this article. The modern EMG machine is a very sophisticated instrument, but for our discussion, we can divide it into three parts. One is the hardware, which contains the stimulator, the amplifier, the filters, and the so-called analog to digital converter. Then you have the control panel, which allows you to make changes to the settings. And then we have the computer, which is also a part of user interface, but more importantly, it is involved in making analysis. We rely on automated marking in nerve conduction studies, jitter analysis, and so forth. And the computer is also responsible for connectivity so that we can review the studies, we can generate the reports, print the reports with or without the waveforms. The primary task of the instrument is it should increase the signal to noise ratio, and it should make signal measurements. Keep in mind that we are recording signals with a very low voltage, few microvolts, and this is embedded in a very high amplitude noise. So we want selective amplification of the neurophysiologic potential and attenuate the background noise. We also make measurements, and we would like them to be reproducible, which means they have low variability. That gives us more confidence in our measurements. And the measurements should also have adequate resolution. This is the bare minimum that one should expect from the instrument. Now, obviously, modern instruments do a lot more things. They can save waveforms, measurements, generate reports and research and so forth. We have already discussed the importance of this, so I will not go into it. I will focus mainly on the signal to noise ratio and making the measurements. So, as far as the standards are concerned, I'm going to approach each of the earlier components by describing how it works, how does it affect the signals, what are the key specifications or the settings, and what are the recommendations for making different procedures. So let's start with the amplifier. We use, as Vincent indicated, a differential amplifier. It has got three inputs, the E1, E2, also called active and reference, and a ground or the E0 electrode. It measures the voltage difference between the E1 and E2, amplifies the difference, and here you can see a 50 microvolt potential now became 50,000, giving it a gain of 1,000. At the same time, we have noise. And here we can see a noise which is 1,000 microvolts. It's 20 times our signal. How can we see this? Well, the noise is common to both inputs, and so therefore their difference should be 0. And therefore we should not see it at the output. That would be an ideal amplifier. In real amplifiers, we also get a small signal output, let's say 500 microvolts. But notice now my noise is much less than my amplified signal. So this is the way we improve the signal to noise ratio. And this ability is measured using the so-called common mode rejection ratio. This is measured in decibels using a logarithmic scale. Essentially, we are comparing the differential gain to the common mode gain. And the rule is that the common mode rejection ratio should be high. That's an indication of a good quality amplifier. We also have internal noise in the amplifier. This is inherent. This has nothing to do with common mode rejection ratio. And we can measure this noise. For example, I have connected all the electrodes together and use the turns and amplitude program. And this can give us the voltage as a root mean square value. This is one way of specifying the amplifier noise. Another method is by measuring the peak-to-peak amplitude. In this case, it is 0.89, and typically they differ by a factor of 3. So when you look at the noise specification, make sure whether you are looking at RMS or the peak amplitude. The peak noise as well as the RMS also depends on the filter settings. So if you make the filter bandwidth less, you will get less noise. So you have to be careful when you assess the noise of the amplifier. Make sure you understand all the settings. Besides the noise, there is another parameter of the amplifier, which is called the impedance. It should be high. This is no longer a problem with modern amplifiers. Another parameter that is not discussed is called the range. How much signal can an amplifier manage and amplify? It has a limit, and that is shown over here. This is called saturation. Notice the flat line over here and flat line over here. So we don't want signals to saturate, because if you have saturation of amplifiers, it takes a long time to get out of saturation. That's how you get large stimulus artifact. So as an engineer, my rule of thumb is that the amplifier range should be 2 times the amplitude of signal and artifact. So that way you don't saturate the amplifier. And sometimes we get baseline drifts, in which case we may want to increase the range of the amplifier. This typically occurs when the low filter setting, the low frequency value is very low. So to summarize, the amplifier should have high common mode rejection ratio, low noise, high input impedance, and a dynamic amplifier range that can be customized based on the application. I do not like to use an amplifier range less than 2 millivolts. This is my personal opinion, and that's why I highlight it over here. We use electrical stimulators. The commonly used settings are the stimulus duration and stimulus intensity. The commercial systems, they have a range, they have a limit on this of 400 volts or 100 milliamps. The stimulus duration varies from 0.05 to 1 milliseconds. I emphasize the duration of 0.02 because some laboratories also use this for nerve block injections. And I think that's where a low value of duration is more suitable. The rate is usually not varied in most testing. We can use it in constant voltage or constant current mode. Constant current mode is the new standard because it allows us to detect high impedance at the stimulation site. So it gives us a feedback when we are making technical errors. Resolution is typically not important in routine conduction studies. We stimulate at supramaximal intensities, which is quite high. We rarely work with threshold intensities other than in research. So that's when the resolution of our stimulus increment becomes critical. And this is something that can be changed on the instrument itself. We got 2 shapes, monophasic and biphasic. Biphasic previously was not common, but now it is becoming standard. It reduces stimulus artifact. And we can also have different patterns, a single stimulus, double stimulation if you want to look at excitability, or even neuromuscular transmission defects, conditioning stimulation to study excitability. Again, this is for research. You don't need it for the routine studies. And a trained stimulation, for example, if you are going to do repetitive nerve stimulation. Filters affect the waveform. We can see them on the instrument. There is a low number and a high number. This is called a bandpass filter. The high-pass filter is associated with the lower number. So 3 Hertz and above will pass through. and the low pass is characterized by the high frequency. This removes noise and interference, but also affects our waveforms and measurements. Reducing the bandwidth reduces the noise, but also reduces the amplitude, and this also affects latency and duration, and therefore it is important to standardize these filter settings. Analog to digital converter takes the analog signal and creates a record or a list of numbers which represent voltage values. It's like a movie camera, which takes about 24 to 30 static frames, but when you play it back in the regular speed, it looks continuous. So the important thing over here is how many pictures you are taking per second. And this is called the sampling interval, which is the time between two different samples. And dividing it into 1 second gives us the rate. If you reduce the sampling rate, you lose amplitude, you lose peaks, the signal appears very smooth, you have a loss of high frequency, and that's called aliasing. So how do we avoid aliasing? In signal processing, there is a so-called Nyquist Shannon criterion, which says look at the highest frequency, and your sampling rate should be at least twice that value. So if the high frequency setting is 10 kilohertz, we should sample at least 20 kilohertz. As an engineer, I prefer to go at least 4 or 5 times the highest limit. Another specification of the A to D converter is the number of bits. It should be 16 or more. This is all available in most systems. So now let's put all of this together and look at the optimal settings. I will just take a few cases, not all of the different procedures. Let's start with the amplifier range. As I indicated, you not only have a signal which is low amplitude over here, just about 30-40 microvolts, but look at the artifact. That can be much higher. And we don't want amplifier to saturate. And that's why I like to use a range of -2 to +2 millivolts. As I indicated, I like to have a headroom by a factor of 2. Filter settings, here we have some variation, 10 to 20 hertz for the low frequency, 2 to 5 kilohertz for the high frequency. This will affect our measurements slightly. The gain should be adjusted, but even though we adjust it, it's not a significant variation. Typically, we measure it at 5 to 20 microvolts. Once in a blue moon, you may want to go to 100 microvolts. The largest potential that I have recorded was 500 microvolts. That was a stimulation in the palm and recording at the wrist on a median nerve. So that's more of an exception. Sweep is important. Again, this goes back to the quality assessment that Vincent referred. If the signals are presented under standard conditions, it's much easier to assess their validity. The recommended sampling rate is 20 kilohertz. There is an asterisk indicating that I'm going to come back to this a little bit later. I have some second thoughts about this recommendation. And this is the stimulus duration. 0.1 milliseconds is typically used for sensory nerve conduction. And these days, we are also using the biphasic stimulation to reduce the stimulus artifact. Needle EMG, we have a lot of variation. So the amplifier range can be -25 to +25. Filter settings, there is a variation depending upon the application. Are we doing quantitative analysis? In which case, the low frequency could be 3 hertz for the duration measurements. For the routine studies, it could be 30 hertz and so forth. We adjust the gain and sweep as necessary. Sampling rate, as I indicated, I like to have it about 5 times the highest frequency. So if this is 10 kilohertz, this should be 50. And I also like to use what are known as the dual time base. So you can see the signal at a fast sweep, you can see the waveform, and you can see it at a slow sweep, which allows you to assess the firing pattern. Here is an example of SSEP. Just wanted to make sure we cover all the bases. Note that my amplifier range is high, although the signal is low, because at the beginning, we can have an artifact. In EPs, we have a better standardization of filters compared to nerve conductions. We have the display gain, but we also have another gain setting which allows us to see the live activity. This is the so-called monitor signal that allows you to see the EMG artifacts or other interferences, which is set at a different scale, 20 microvolt or so, although the waveforms are seen at 2 microvolts. Let's take another example. This is cognitive evoked potential P300. And in this case, notice that our low frequency setting is 0.1 hertz. So this is where you are going to have baseline shifts. So although the signal itself is low in amplitude, you need to have a high amplifier range. And this is where you have the possibility of amplifier saturation. So I often like to use a command on the instruments, which is called D-block, so that you can recover the amplifiers faster and continue with the testing. And once again, you can have different types of scales or time bases. In this case, it is 100 milliseconds per division because the P300 is going to be 300 milliseconds after stimulus, roughly. Sampling rate is 1 kilohertz because my high frequency setting is 200 hertz, so 5 times it. So these are the kind of summary settings that will allow you to optimize your waveform display. It allows you to assess the quality of the recordings, visualize the potential, and so forth. The green ones are where I am very happy. The other ones, I have got some additional thoughts that I'm going to share with you in the last few minutes. I know we always have standards, but standards can always be improved upon. So my focus is going to be on signal measurement. Signals should be reproducible and they should have adequate resolution. And this is something that I have recognized only very recently, within the last 2 years or so. So the example I'm going to use is an ulnar nerve conduction study. You can see wrist below elbow, above elbow. Here are my conduction velocities in the forearm, 55, across the elbow, 39. The difference is 16 meters per second. This can be useful to assess lesions across at the elbow. So here is a recording in my elbow. At the top, you can see the wrist stimulation. Here is the above elbow stimulation. And here are 7 stimulation, consecutive ones with below elbow. And what you notice is that the latency is not constant. It changes. This is something that you have seen on your own machines, but I don't think we paid much attention. And this represents the sampling rate of our system. So you can see the latency is changing by 0.02 or 0.03 milliseconds. If you look at the velocity, it changes by about a meter per second on successive stimulation. Is that acceptable? I think yes. Our normal range of velocity could be like 50 to 65. So 1 meter per second is an acceptable variation. We get a variation in the velocity difference of about 2 meters per second. But if I were to cut down on the sampling rate, the waveforms look exactly the same, but now look at the latency variability, 5.94, 6.04, 6.15. This is an indication of the sampling rate. If you look at the velocity, now it can change as much as by 4 meters per second on successive stimulation. That's 1 standard deviation of our reference data. So if we are going to use things like z-scores, we really need to get to the bottom of what's the resolution of our velocity. And if you look at the velocity difference, 4.4 is normal, 12.5 is abnormal. And all of this happened using exactly the same settings, but on 7 consecutive stimulation. So this is something that I have been thinking very aggressively these days, that perhaps we need to go back and look at our standards and focus on the sampling rate. The Nyquist criteria is heavily focused on the amplitude. It doesn't talk about the time differences. And on instruments, we do subsample the signals to save the data. So I think this is something we need to look for future. What is the resolution of the saved data and how it affects the velocity measurements? When we do orthodromic studies, mid-palm stimulation, many times we accept 0.3 as an upper limit. But if our sampling rate is 10 kilohertz, sampling interval is 0.05, that means you have an inherent variation of 0.1 with the ulnar recording, 0.1 millisecond variation with median stimulation. Our variation is 0.2, and our upper limit is 0.3. We certainly want higher resolution to make these measurements. So once again, I go back to the Nyquist criterion. We were very focused on amplitude. I think now we need to focus on the time differences. Similarly, with the brainstem auditory evoked potential, if we recommend a side-to-side difference of 0.3, then I believe our resolution should be 1/10, 0.03 millisecond. I think let's look at filter settings. This is a sensory nerve conduction where we typically use an upper frequency of about 3 to 5 kilohertz. But wait a minute, if you look at the signal, it has a short duration, only about 2 to 3 milliseconds. This is a high frequency signal, and yet we use a lower setting for the high frequency. You may want to try this. Open the filters completely, and you will notice that you get far better sensory nerve responses than using our traditional settings. I know we used a lower setting of high frequency because of noise, but I think our amplifiers have gotten better. We can smooth waveforms, we can average them. I think we need to look at our standards in a few years. And my final example is we often use signal averaging, but when do we stop averaging? Our criteria has typically been subjective or based upon the number of sweeps. These recordings look fairly good, but what is the signal to noise ratio? On the right-hand side, you can see the waveform, and the purple line is the noise. And you can see the signal to noise ratio is terrific on the top trace and the bottom trace, but it's not so good on the middle trace. So we really need to focus upon noise. The interesting thing is that audiologists already have standards on how to measure noise in average potentials. I think we can learn from them and incorporate them into our EMG nerve conduction studies. So to summarize, instrument settings affect noise and measurements. The best strategy is to reduce noise before you make any kind of recordings. That's a part of instrumentations and other things. I will not go into it. We have proposed settings to maximize signal to noise ratio. This is not the gospel. I mean, that's why I indicated that with the change in technology, with the change in our hardware, I think we can get even better resolution in the signal. We can get better amplitudes. So whatever we have proposed is based upon maximizing the signal to noise ratio. We should look at some changes to this in future. Whatever settings you do, use them in a consistent manner. Because if you change the filter settings, it changes your amplitude. It can change your latency's duration. So we have some recommendations. If your measurements or settings are slightly different, don't worry about it. Just use it in a consistent manner. Keep in mind that the normative data will depend upon settings. So it's not a good idea to just abruptly change your settings. And my thinking these days is I think now we have technology by which we can sample signals at a high rate, and we should be able to make better analysis of latency and velocity assessments. Thank you, and I'll be happy to take a few questions.
Thank you very much, Sanjeev. A very clear presentation, as always, from you. I'm just waiting if there are any questions coming in, or if there are any comments by the panelists, you're welcome. Meanwhile, I can ask you, I think the engineers are becoming a rare breed in neurophysiology laboratories. We are happy to still have two at our institute, but in general, I think doctors have to rely on their own knowledge and when deciding how to use the technology. when buying a new machine, do you have any recommendations what to look for? Because usually we feel quite, I mean, we have problems deciding which machine is better. Are the industry standards high enough so we can trust all the providers, or are there still any technological tricks that we need to know of or be aware of?
I would say that the instruments that are offered today, and I'm not talking about as a Natus employee, I think all equipment on the market are pretty good. There has been a significant change in their instrumentation in terms of the common mode rejection ratios, the availability of filter settings, the ability for signal averaging, the biphasic stimulations. I think if you compare the instruments compared to 10 years ago, I think all of you will be surprised, regardless of the brand of the system that you are using, would be nice. The thing that I always look for is the marking algorithms, because to me that a lot of people depend upon automated marking. How good is it? Are you able to change it? And now I'm becoming more and more aware of the sampling rates of the saved data. So I think that's where we may see some differences in different systems. I think ultimately a system should be flexible. It should be more user-friendly, that allows you to make automated measurements. More important, it allows you to override automated measurements. That's the way I look at the system. But I think the instruments overall are getting better, and they will get even better. And we will have even better quality signals. So the typical specifications that I just indicated, signal to noise, the instrumentation noise, the common mode rejection ratio, the sampling rates, these are the kind of things that we need to look at.
Okay, thank you very much.